I'm now going to pass it over to my colleague, John Novak. He is going to share his screen. And so we're remote now as a team. So I'm going to allow John to share his screen and we'll continue the presentation. So John, over to you. So John started his career as a PV designer for a commercial developer called GeoPeak Energy. In that role, his scope covered not just design, but most aspects of the solar project's workflow, okay? He also worked at NRG, where he designed over 2,000 systems nationwide and became a leading voice on quality control for projects. After experiencing a lot of the solar inefficiencies firsthand, he left to found and build Scanifly. John is OSHA and IREC trained and is a Part 107 drone pilot license. He also has a background in landscape architecture, horticulture, and GIS. So when it comes to understanding all of the aspects of solar and drones and putting it together to maximize imagery, I think John is the perfect person to walk us through these next items. So John, I'm going to turn it over to you.
Great, thanks for the intro, Jason. I really appreciate that. Hey there, Scaniflyers. Thanks so much for your time today. Really appreciate it. So Scanifly was born out of the idea of using reality capture and 3D mapped environments to accelerate project development and bring this real world context to the assessment and design process, where you can design for any roof and design for any structure, existing and proposed. So why reality capture? Well, when you assess the site and design a PV system using a 3D mapped environment, you have this canvas that provides real world context. And that real world context is super important when designing hyper accurate PV systems. So how can we capture reality? How can we digitize the real world so we can build solar PV on top of it? Well, let's capture reality using a drone, then design and analyze using a 3D mapped environment. This will provide that real world context that we need. So one method for 3D mapping the real world is called photogrammetry. And photogrammetry is the art and science of extracting 3D information from photographs. This involves taking overlapping photographs of an object, structure, or space and converting them to a 3D model. For this example, the artist used an array of DSLR cameras and the photogrammetry method to create a 3D model of this race car driver. Super cool. Here's another example where the artist used the photogrammetry method to help design this World War I memorial in Washington, D.C., which I believe won the design competition and is scheduled to be built sometime next year. Now, if you look closely, you can see the soldier and the nurse that are being 3D mapped here right there in the memorial. Really cool, really awesome. So here's another great example of photogrammetry. Former President Obama was the first American president to be 3D mapped. Now, there's a really great informative video that whitehouse.gov published about this. So let's watch it.
We're here at the White House working with the Smithsonian Institution on creating a 3D presidential portrait. And the system that we've brought to be part of this process is called our mobile light stage. It's right over there, and we're setting it up right now so that it can be used to record almost certainly the highest resolution digital model that's ever been made of a head of state.
The inspiration for the project of creating a 3D portrait of President Obama really comes from the Lincoln Life Mask in our National Portrait Gallery. And I have a Lincoln Life Mask with me today, and they're called life masks because these were directly taken from his likeness. So there was plaster put on his face, there were 2 little holes poked where the nostrils were so he could still breathe. And seeing that made us think, what would have happened if we could actually do that with a sitting president? Using modern day technologies and tools to create a similarly authentic experience that connects us to history, to connects us to a moment in time, and connects us to a person's likeness.
So the process should go relatively quickly. We will invite the president to sit down. he will be surrounded in front by 50 custom-built LED lights, 8 high-resolution sports photography cameras, and an additional 6 wider-angle cameras. In about 1 second, as he holds his presidential pose, he will be illuminated by 10 different lighting conditions, which will change the polarization of the light, the directionality of the light, and will give us everything that we need to understand the shape of his face and how it transforms incident illumination into the images that we see of him. 10 years ago, it was just barely possible to think this could be done.
So here we have a structured light 3D scanner, and we're using this to scan the president. They're handheld, they're flashing a fringe pattern of light, and there are stereo cameras recording how that fringe pattern forms over geometry, or in this case, the president's face.
The president getting his likeness scanned, as cool as that is also about a broader trend that's going on, and that is the third industrial revolution. It's the combination of the digital world and the physical world that is allowing students and entrepreneurs to be able to go from idea to prototype in the blink of an eye.
It's been a few days since we've 3D scanned the president, and we're looking at some raw data on screen right here. So this is the data that came out of the handheld scanners that Adam Mattel and I were using to scan the president.
Well, this is the first bust that's created of a head of state from objective 3D scanned data. So this isn't an artistic likeness of the president. This is actually millions upon millions of measurements that create a 3D likeness of the president that we can now 3D print and make something that's never been done before.
All right. Really cool video. Really exciting stuff there. Now, if we take a closer look at the array that they used to 3D map former President Obama, you'll notice the cameras are positioned strategically at different heights and different angles. And this, this could be thought of as okay, we're 3D mapping a building, and if the building was here, that these cameras, right, the way that they're positioned, these could be thought of as different altitudes, right, as we're flying around the building, capturing more data, different angles and different altitudes here. Now, the reason for doing this is this maximizes the amount of coverage and ensures all areas of the object are 3D mapped in the finest detail. Even more important are the 50 LED lights in this setup, which are there to create the perfect lighting environment and create multiple lighting environments to 3D map the object as best as possible. So why use these examples here? So after all, we have zero control over the lighting environment, and we're not using an array of cameras, right? We only have one camera, and it's attached to a flying robot. And even though we only have one camera, the concept is still the same. We're using a batch of overlapping images to create a 3D model. So since we can't control the sun and the clouds, we need to understand more about how the camera works and how to take high quality photographs to create high quality 3D models.